On this question, we're given the equation y equals x cubed times the square root of 2x plus 1. And with this equation, we want to find y prime, which is the derivative of this equation, the derivative of y. So before I start calculating the derivative, I want to analyze the equation to see which rules I might be using to calculate the derivative. So I can see here that I have an x cubed. This is x raised to a power, so I might be using the power rule for derivatives. So the power rule for derivatives is the derivative with respect to x of x to the nth power is n times x to the n minus 1. So that's our shortcut for calculating the derivative of x to the power. And then I notice over here that I have a square root of 2x plus 1. Now I want to keep in mind that with algebra, I can rewrite this square root as a power. So let's rewrite it using algebra. So this is y equals x cubed. And that square root is the same thing as the 1/2 power. So this is going to be 2x plus 1 to the 1/2 power. So because we have a power there, that's another indication that we might be using the power rule. Another thing I notice is that I've got multiplication. And multiplication is a product, and I've got a variable inside of this factor and a variable inside of this factor. So I'm going to be forced to use the product rule for derivatives as well. So the product rule for derivatives, if you have the derivative with respect to x of, let's say, a product, f times g, the way we calculate the derivative of a product is to do the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. And there's one more rule that I'm noticing that we're going to have to use here. And what I notice is on this factor right here, I have an outside function, which is the power, and I have an inside function, which is 2x plus 1. And because I have an outside function and an inside function, this is something that we call a composition. Because I have a composition of two functions, I'm also going to have to use the chain rule to calculate the derivative. And the chain rule says this: if you have the derivative, and this time we're doing the derivative of a composition, that's when you have an outside function and an inside function. We follow this pattern here. We calculate the derivative on the outside function. We're going to leave the inside function the same, and we chain, which is why this is called the chain rule. Chaining is multiplying by the derivative of the inside function. So these are all rules that we're going to use in order to calculate the derivative of our equation, y equals x cubed square root of 2x plus 1. So let's rewrite it and start calculating the derivative. So I've already rewritten it with algebra. That would give me x cubed times 2x plus 1 to the 1/2 power. Now the first rule that I'm going to use is going to be the product rule. have a factor of x cubed and a factor of 2x plus 1 to the 1/2. So the derivative following the product rule will be the first factor times the derivative of the second factor. So I need to calculate the derivative of 2x plus 1 to the 1/2 power. I'm not going to calculate the derivative right now because I want to make sure that I finish up the entire pattern for the product rule. So I've got x cubed, the first factor, times the derivative of the second factor, plus the second factor of 2x plus 1 to the 1/2 power times the derivative of the first factor. So I want to take the derivative of x cubed. So I've written out the product rule, and I still have some pieces that I need to calculate the derivative of. I need to calculate the derivative of 2x plus 1 to the 1/2 power, and also the derivative of x cubed. For the derivative of 2x plus 1 to the 1/2 power, I need to use the chain rule because it's the composition of two functions. So using the chain rule, the outside function is the power, and the inside function is 2x plus 1. So to follow the chain rule, I need to calculate the derivative on the outside function. So because the outside function is a power, I'll follow the power rule. The power rule is we multiply by that power, and then we're going to take 1 away from that power. So we do 1/2 minus 1. We leave that inside function alone. So following the chain rule, I'm leaving the inside function alone. And then I need to multiply by the derivative of the outside function. Excuse me, the inside function. I need to calculate the derivative of g of x. I need to calculate the derivative of 2x plus 1. And that's the chaining part, and this is multiplication. So I'm going to continue on. So that's the derivative. I still have that last part to calculate, but I'm going to continue on with the rest of this. Plus 2x plus 1 to the 1/2, and I need to calculate the derivative of x cubed. The derivative of x cubed, we'll use the power rule to calculate that, and that would be 3x squared. I'm going to copy all this down. (1/2 minus 1 would be negative 1/2. And I need to calculate the derivative of 2x plus 1. The derivative of 2x plus 1 is 2. And here I'm copying the rest of this down. 2x plus 1 to the 1/2 power and 3x squared. So at this point, we have calculated the derivative. It's a little bit messy, so I'm going to use some algebra to clean it up. So I notice that I have a 1/2 and a 2 that will cancel each other out because 1/2 times 2 is 1. And let's see, I can do a little bit of factoring here. I have x cubed and x squared, so I can factor out an x squared. I also have 2x plus 1 to a power and 2x plus 1 to a power. So if I factor out 2x plus 1, I'm going to factor out the lower power, which is 1/2. And when I factor that out, I'm factoring out an x squared. So if I factor an x squared out of here, I'm left with an x. And I am factoring out this whole thing right here, so that's gone. And then over here, I'm factoring out this x squared, it's gone. I still have that 3. And for the 2x plus 1 to the 1/2 power, this is the part that confuses most people. We would have 2x plus 1 to the 1/2 divided by 2x plus 1 to the negative 1/2. When you're factoring it out, you're dividing it out. So I took what's there divided by what I'm factoring out, and I'm going to use that to figure out what's left. So because they have the same base, we can subtract the exponents to see what's left. So if I subtract those exponents, 1/2 minus negative 1/2 is going to leave me with a 1. We've got x squared times 2x plus 1 to the negative 1/2 and x plus 3, and this is 2x plus 1 to the first power. So a couple other little things. We can now distribute that 3. That would be x plus 6x plus 3. And because we have a negative 1/2 power, I can move that factor to the denominator and also turn it back into a square root. So we have x squared times 7x plus 3 over the square root of 2x plus 1. Let's zoom out so we can see the whole derivative process. For f of x equals 3x squared minus 4x minus 5, we want to find the equation of the tangent line when x equals 1. We're going to write that equation in slope-intercept form. So when we're looking for the tangent line will be some equation y equals mx plus b. And the slope of the tangent line, that m for the tangent line, so let's say that's m sub tan, the slope of the tangent line, will be the derivative of our function, and it's going to be evaluated at whatever particular x value we're using. So we can find the slope of the tangent line by calculating the derivative and substituting that x value in. But we're also going to need a point on that line in order to get the equation. So in order to get the y1 that we're going to use in our point slope form, so point slope form is y minus y1 equals m times x minus x1. So in order to get this y value, we need to evaluate our function at that x value. So we have a couple pieces to figure out, and once we figured out the slope of the tangent line and also that y value, we're going to be able to create the equation using this point slope form. So let's find the y1 first by doing f of 1. That's 3 times 1 squared minus 4 times 1 minus 5. That's 3 times 1 minus 4 minus 5. We have 3 minus 9, that's a negative 6. So we have the point 1, negative 6 that's on our line, and that's our x1 and y1 for this particular function. So then we want to find the slope of the tangent line. So I need to calculate the derivative. And the derivative of 3x squared will be 6x. And the derivative of a negative 4x will be minus 4. And the derivative of 5 will be 0. So then I'm going to find that slope by evaluating that x value. So we have 6 times 1 minus 4. That's 6 minus 4, which is 2. So now we have the slope of the tangent line and a point on the line, and we're going to be able to find the equation of the line. So y minus y1 equals m times x minus x1. We have y minus negative 6 equals 2 times x minus 1. Y minus a negative, that's the same thing as y plus 6. And I can use the distributive property. 2 times x is 2. 2 times negative 1 is negative 2. And then I want to subtract 6 on both sides. And this would be my equation in slope-intercept form. That's 2x minus 8. So we found the equation of the tangent line to be y equals 2x minus 8. On this question, we want to find the limit of our function f of x equals this piecewise defined function. And the piecewise defined function is 3x minus 4 when x is not equal to 1, and 2 when x is equal to 1. And it looks like that we're interested in the limit near 1, which is our distinguishing spot between when to use these two equations. So we want to find the limit of f of x as x approaches 1 plus. So in this example, we are working on a one-sided limit, and that one-sided limit is 1 plus. 1, which means just a little bit more than 1. So this particular piecewise defined function has a unique way of identifying when to use each equation. And the way it's unique is that the second equation is only ever going to be used when x is equal to 1. Every other value of x, we should use the first equation. So since we're interested in the limit as x is getting closer to 1, that means that we're going to use the first equation, because we use this first equation anytime x is not 1. Here we want x to be more than 1, and if it's more than 1, it's not 1. So we're going to use the first equation to identify this limit. So that's going to be 3 times 1 minus 4. And that's 3 minus 4, which is negative 1. So in addition to this, let's look at the limit on the other side. The limit as x approaches 1 with the minus of f of x. So this is telling us that x is less than 1. So once again, we would use the first equation to find this limit because we only use the second equation when x is exactly 1. Here, x is less than 1, so we'll use that first equation. 3 times 1 minus 4, which is 3 minus 4, and that's negative 1. So now that we've done the one-sided limits, we can do what I like to call the overall limit, the limit as x approaches 1 of our f of x. And on this one, our limit is approaching 1. And when we approach 1 in this way, we mean from either side. So this has got to be both more than 1 and less than 1. And we've already worked these out. For more than 1, we know the limit approaches negative 1, and for less than 1, we know the limit approaches negative 1. So these are agreeing with each other, and so from both sides, the limit is approaching the same value of negative 1. So the limit as x approaches 1 of f of x is negative 1. We want to find the derivative of the function f of x equals e to the x over x plus 5. Before I start calculating the derivative, I want to think about what rules I might be using. So the first thing I notice is this fraction bar here. So I might need to use the quotient rule, which deals with fractions. So the quotient rule is the derivative of f over g. So when we have a fraction, we follow this shortcut, this pattern for calculating the derivative. We're going to take the bottom function multiplied by the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So I'm probably going to use the quotient rule because of the fraction, and then in the numerator I notice e to the x. So I'm going to use the rule for the derivative of e to the x. The derivative of e to the x is e to the x. So let's calculate the derivative using the quotient rule. My function is f of x equals e to the x over x plus 5. The derivative, I'll follow the quotient rule, is the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function over the bottom function squared. So I followed the pattern of the quotient rule, but I didn't calculate the derivative on these individual pieces yet. So I'm going to go back and calculate those. The derivative of e to the x is e to the x. And the derivative of x is 1, and the derivative of 5 is 0. So the derivative of x plus 5 is 1. I'm copying the rest of this down. And we have a little algebra. We've calculated the derivative, but we have a little algebra so we can simplify more. I can distribute that e to the x. That's x e to the x plus 5 e to the x minus e to the x. Then I have some like terms here. I have a positive 5 e to the x and a negative e to the x. Those combine together to be 4 e to the x. And on this one, we do have a common factor of e to the x, which we can factor out, and that would leave us with x plus 4, a factor of x plus 4, over the x plus 5 squared. So we found the derivative of e to the x over x plus 5 to be e to the x times x plus 4 over x plus 5 squared. Thank you for checking out my videos. Have a great day.